Okay, this video is part 6 of obesity causes, and the focus for this lecture will be theories of diabetes causation by Drs. Yamashima and Dr. Taylor. The reason it matters is things that cause diabetes tend to be things that cause insulin resistance. Insulin resistance causes obesity. So it's all part of the same thing. Okay, so the first slide here, we'll just talk a little bit about, what is a fatty acid. So fat is made out of fatty acids. Saturated fat has no double bonds. It's saturated with hydrogens. Okay, the typical saturated fat is palmitic acid, C16, meaning 16 carbons, and 0 as in 0 double bonds. MUFA means monounsaturated fat. There's the mono. And that means it has one double bond. That's what mono stands for. The classic monounsaturated fatty acid is olive oil. And it's C18, meaning 18 carbons with one double bond. And W9, the W means like omega, so it's at the 9th position from the methyl end over here. Okay, so this would be a saturated fatty acid. And here's a carboxylic acid. That's why it's called an acid. And that will be polar with a charge on it. Here is the hydrophobic component, the hydrocarbon chain of carbon and hydrogens, and that is nonpolar, meaning soluble in oil. Polar and hydrophilic means soluble in water. Amphipathic means that it's soluble both partly in water, partly in oil. And that's relevant. It's like an amphibian, can live on land and water, and things that have a component of both can function as detergents or emulsifiers, meaning that they can pull something from a lipid phase into the aqueous water phase, and that's going to be important later on and that's real important just for knowing in general about fatty acids. Okay, now here's an example of MUFA, one double bond. Here's a PUFA with two or more double bonds. And then there's a carbon in between the double bonds where there's no double bond attached to it. And this carbon is called the methylene bridge because it's a C and there's going to be an H2 on it. That's a methylene group. So anyways, the relevance is because double bonds are pulling on the electrons, this has only a weak grip on its electrons, and this hydrogen can be plucked off. And that can initiate a cascade of reactions called lipid peroxidation. This being the carboxylic end is also called the delta end. You'll sometimes see that nomenclature. In general, though, for nutrition, talking about fatty acids, it's much easier to talk about the methyl end. And the methyl end is called the omega end. And it's often symbolized like with a little W most commonly. So this writing right here, C18 colon 2 would be 18 carbons with two double bonds. And then the omega, the bonds are at the 6th and the 9th position, starting from the methyl end. Okay. Okay, now here is a PUFA fatty acid. You got an omega-6 fat because the first double bond's at the 6th position. Then here's the methylene bridge. This hydrogen can be plucked off, leaving an electron in an unpaired orbital, and oxygen will combine with this to make what's called a peroxyl group, and there's still an unpaired electron, so this is still a free radical. And this can initiate a chain reaction that can destroy plasma membranes or other membranes. The more double bonds you have, the more prone the fatty acid is to undergoing lipid peroxidation. And lipid peroxidation occurs with PUFAs. And like I said, the more double bonds on there, the worse it gets. And it's a major big problem with omega-6 fats, like in all these cooking oils. And they'll have a tendency to produce this chemical here called HNE, hydroxynonenal. And what this article here was, I haven't specifically read about the aldehyde lipid peroxidation byproducts of omega-3s, but I would expect that it would be a problem for them too, because they'll have multiple double bonds. ALA has 3 double bonds. So this was a study where they just simulated the conditions in which people purchase omega-3 oils and omega-6 oils, and they found that there was an increase in these toxic products. And so either with omega-3s or omega-6, it was of concern. But I haven't really read that much about it because to me it's an obvious thing I wouldn't want to do. So that's why I haven't read about it as much as I could. Perhaps eventually I'll be motivated to read about that some more. Here's an example of hydroxynonenal. So let's just go through the nomenclature of it. You're going to hear about this all the time. If you read about lipid peroxidation, you will hear about it all the time. Here's one reference of a paper, 4-hydroxynonenal lipid peroxidation product, because this is a major toxic aldehyde that does a lot of damage to the human body when people eat omega-6 cooking oils. So here's the nomenclature. Non means 9, so non is 9 carbons, okay? En means double bond, so here's the double bond on it. Al means aldehyde, so it's an aldehyde, meaning that there's a ketone or a carbonyl group, then it's just attached to a hydrogen, rather than if it was a hydroxyl group here, then that would be a carboxylic acid. Okay, it's called 4-hydroxy because the hydroxy group, the OH group, that's located on carbon number 4. So that's why it's 4-hydroxynonenal, and it's usually abbreviated HNE. HNE is a major problem because it inhibits ATP synthase in the inner mitochondrial membrane for ATP production. Anything that damages mitochondrial production of energy will tend to cause insulin resistance, and that's not good. When you hear the word oxidative stress, that means you've got more oxidants than antioxidant capacity. Small amounts can be hormetic, even beneficial, but when they're present in large amounts, they start to cause these cascading chain reactions that damage a lot of normal tissue. And in particular, we're going to see that omega-6 cooking oil related hydroxynonenal can damage our hypothalamus hunger center, leading to difficulty controlling appetite. It can damage the hippocampus, leading to worsened memory and cognitive decline, and it can also damage the pancreas beta cells. Those are the ones that produce insulin and cause insulin resistance and diabetes. Okay, and this is sort of a major thing. HNE is a mitochondrial toxin. Okay, so this comes from the work of Dr. Yamashima. Dr. Yamashima's name is Tetsumori Yamashima. He's a Japanese neuroscientist, and he was tasked with the job of trying to figure out why the incidence of dementia in Japan was going up much faster than expected. And he studied a lot these omega-6 cooking oils, and he came to the conclusion what's happening is the omega-6 cooking oils undergo lipid peroxidation, producing HNE, hydroxynonenal. And now, first of all, let's talk about what normally is done by HSP. HSP means heat shock protein. Heat shock protein has one job. It functions like a chaperone. These little black things that look like sperms, those are dysfunctional proteins. And the heat shock proteins carry them to the lysosome where they can be broken apart, sort of recycled. Think of it as a recycling plant. The heat shock proteins also bind to the membrane of the lysosome and they stabilize it. So they got two jobs that are both related to recycling old dysfunctional proteins inside of the cell, like let's say in a neuron. Now here's the problem. When hydroxynonenal is present, it'll bind to the HSP. So here's the HSP binding to hydroxynonenal, and that combination of HNE bound to HSP activates a proteolytic enzyme in the cytoplasm called calpain, and calpain will cleave the HSP, and it'll thus render the HSP dysfunctional. Now the HSP can no longer chaperone dysfunctional proteins, and the HSP can no longer stabilize the lysosomal membrane. So the lysosome will break apart, and its digestive enzymes will kill the cell. So that's a big deal. And this is a mechanism by which the omega-6 cooking oils can lead to brain damage. And they can also cause damage in the pancreas. And they can cause brain damage in the memory center and the hippocampus, leading to cognitive decline. They can cause brain damage in the hypothalamus hunger center, leading to inability to regulate hunger effectively. And, like I said, damage the pancreas beta cells, leading to diabetes because you can't make insulin. Okay, a real quick refresher on mitochondria. Mitochondria are thought to have been taken into bacteria like prokaryotic cells and sort of like the beginnings of life on Earth. And then the mitochondria provides the cell with energy. It has an outer mitochondrial membrane, typically abbreviated OMM. It has an inner mitochondrial membrane, typically abbreviated IMM. There's a space between these two membranes called the intramembranous space. That's typically abbreviated IMS. The center of the mitochondrial membrane is called the matrix, or the mitochondrial matrix. Krebs cycle happens in the matrix. Electron transport happens along the inner mitochondrial membrane. The protons are pumped into this intramembranous space. And this is pretty much how all human life forms the vast majority of its energy. So it's good to know a little bit about it. You don't have to know it in detail, but it's just good to know that the electrons are transported down a gradient towards oxygen, and oxygen is the ultimate electron acceptor. It's got a very high electronegativity, meaning that it really wants to grab those electrons. At these pumping stations called complex 1, complex 3, and complex 4, they pump a proton. The proton is pumped into the intermembranous space, and you gradually build up a very high gradient, like 160 millivolts protons pumped in there. And then the gradient is harvested by allowing a proton to come back into the mitochondrial matrix, and the energy that provides spins ATP synthase, and that is used to add a phosphate to ADP to make ATP. So ADP is adenosine di is in 2 phosphate, to make adenosine tri is in 3 phosphate. And that's how energy is produced in a cell. ATP is the unit of energy in a cell. It's like the equivalent of a $20 bill for humans. Okay, so in a normal mitochondria, here's your OMM, outer mitochondrial membrane. Here's your IMM, inner mitochondrial membrane. The electrons from glycolysis and Krebs cycle are passed to these complexes, complex 1 and 2. And then the electrons are passed down the electron transport chain till they get to oxygen. Oxygen is the ultimate electron acceptor, and it converts the oxygen into H2O, into water. These protons are pumped into this intermembranous space, building up a pressure gradient, electrochemical gradient, and then a proton is brought back in through ATP synthase, and that's called harvesting the gradient to make ATP. Occasionally, you'll get some leakage of electrons. They'll bounce off a coenzyme Q, and they'll bind to an oxygen in the mitochondrial matrix. That always happens in small amounts, and the mitochondria can handle that quite well. They've got an enzyme called superoxide dismutase, which helps to neutralize this superoxide free radical. However, if it becomes excessive, then it can become a problem. Okay, here's an example of when you're getting excessive amounts of superoxide. You can overwhelm your superoxide dismutase. And in the presence of excessive free iron, you can run this reaction here called the Fenton reaction and produce hydroxyl radicals, which can then damage. They can trash the inner mitochondrial membrane through lipid peroxidation. In addition, superoxides can also go down a similar, a little bit different but similar path. They can interact with nitric oxide free radicals to produce peroxynitrite, and those can also damage and trash inner mitochondrial membranes. So the bottom line is you don't want excessive free iron sitting around, and you don't want things inhibiting your mitochondrial proton pumps here. Things like high fat, especially saturated fat. And then just to make a point, there's a lot of things that inhibit electron transport into mitochondria, including glyphosate, the herbicide, cadmium, excessive dietary fat, especially sat fat, lead, fluoride, lead, hydroxynonenal. So all these things, and atrazine does this, we talked about that in a recent lecture. All of these things are going to worsen mitochondrial function and increase insulin resistance. So you avoid, like lead by, eating only organic. You're less likely to have lead in your food. I realize you could still have lead in your food, but you're less likely. Depends what country you buy it from. By eating organic, you avoid GP. By eating a low-fat diet, very low-fat diet, and avoiding all meats and oils, you minimize your dietary fat. By filtering your water, let's say you're drinking water with reverse osmosis, you decrease F-. These are ways to minimize your inhibition of your mitochondria and thus be better able to make energy and you feel better. Okay, so here it is, Dr. Tetsumori Yamashima. And he did some research in Japanese people, and the ones that were most vulnerable were the ones who were most sensitive to drinking alcohol. They had like that Asian flushing syndrome because they lacked like acetaldehyde dehydrogenase type enzymes for processing alcohol. But it still happens in mice and monkeys even if they don't have any of these enzyme deficiencies. And this is thought to be why some people, two problems. First of all, when it damages the hypothalamus, it'll cause inability to regulate hunger. When it damages the hippocampus, he claims that'll cause more dementia. And he called it Alzheimer's. Just call it dementia, though. It's not really Alzheimer's. Okay, here's some slides from the Dr. Yamashima paper. And this is showing neurons in the arcuate nucleus of the hypothalamus being destroyed by these toxic aldehydes, the HNE, like we talked about with that mechanism of calpain proteolytic enzyme activation. So here would be like a normal neuron. You can see the nucleus quite well. And here would be a destroyed neuron. It's you can no longer recognize the nucleus. It's fading into oblivion. And as a person gradually, progressively loses more neurons in their arcuate nucleus of the hypothalamus, one of their hunger center areas, they're going to have less ability to regulate their appetite. Most fat people are fat forever. And he also shows that it happens rather severely in the hippocampus, in the CA1 sector. That's just a part of the hippocampus. And you get the same problem, a loss of neurons. Not good. So this is the hippocampus, the memory center, losing neurons. Again, normal neuron here with its nucleus, relatively distinct margins, and then these dead neurons where they're sort of fading into oblivion, and the macrophage immune system cells are going to recycle them. So there's nothing good about omega-6 oils. You should never eat them. I mean, if you eat them just one day, you're at a party, a business lunch, maybe you have to in that case, but don't make it a habit. Okay, I would recommend never eat it. As much as you can, avoid them. Okay, hydroxynonenal causes Langerhans cell degeneration in the pancreas of Japanese macaque monkeys. And again, this is Dr. Tetsumori Yamashima's research, Japanese neuroscientist. So Langerhans cell, he means the beta cells of the pancreas that make insulin. And this is, I think, the reason why persons of Indian descent, they have a tendency to eat a lot of fried food, because I always think of them as being real healthy. I know all these skinny male doctors, they're friends of mine, but when they're eating a lot of fried foods, a lot of people in India, they're skinny, but they still got diabetes, and I think this is probably the reason. Am I 100% certain? No, I'm not, but it's the best explanation I've come across so far, is that's what seems to be doing it. Okay, this is one study where he injected intravenously typical diet-related amounts of hydroxynonenal, and to see if he could mimic the blood levels of H&E he sees in humans, and he was showing how that destroys beta cells in the pancreas, and he goes through that whole same mechanism we just talked to with the heat shock proteins, and disruption of the lysosomes, activation of proteolytic enzymes. And these are healthy primates. They didn't have any of these enzyme deficiencies like the Asian flushing syndrome patients. So here's the papers on these subjects. Here's the Yamashima paper. Here's a paper by someone else talking about these things. One sec here. All right. Causes of beta dysfunction. Some of these we talked about before. Eventually the beta cells die and they can't be replaced. Sometimes early on they simply de-differentiated and stop producing insulin. Dr. Tetsumori Yamashima did all this great research on this. There's other theories that, again, if you catch the type 2 diabetes earlier, you got a good chance to reverse it. I joke, I made something I call the Rogers Law. The more profitable it is to manage a disease, the less likely a cure will ever be discovered. And I think it's kind of funny. If you go to all the foundation websites, which theoretically claim to be helping these poor, pathetic patients, the foundation website will always tell them, no one really knows what causes your disease. We're working on it. Please give us more money for research. They don't tell them go very low-fat vegan, okay? And lots of these type 2 diabetics reverse it, okay? If you catch it early, you can reverse it in almost 100% of type 2 diabetics. McDougall will say 100% of them if it truly is type 2 diabetes. This guy, Roy Taylor, MD, he won the Banting Award in 2012. Banting Award's like for the best diabetes researcher. He basically, proved that all these patients being cured. And we're going to talk about Roy Taylor's work here in a moment. So we just talked about Yamashima's work. Now we're going to talk about Roy Taylor's work. Okay, Roy Taylor was friends with Gerald Shulman, and, these guys are brilliant guys. Genius level research here. They were working out at Yale, and Shulman especially worked with nuclear magnetic resonance spectroscopy to map out the chemistry of the individual skeletal muscle cells, and he proved that the first thing you could find in a skeletal muscle cell when there's insulin resistance is accumulation of fat. Roy Taylor subsequently used MRI, magnetic resonance imaging of the entire body, and he showed that accumulation of fat in the liver, like fatty liver, is basically diabetes of the liver, okay? And then fat accumulation in the pancreas is diabetes of the pancreas, in the sense that's when you're losing your beta cells. And any radiologist can tell you they very often see fatty atrophy of the pancreas, especially the head of the pancreas. They probably won't be aware that that's indicating diabetes, that you've lost your beta cells to make your insulin. It's been noted that when a person is progressively getting fatty liver, they tend to drift up their ALT enzyme. That's a liver function enzyme. And that ALT drifting up is an indicator that they are headed towards type 2 diabetes. Fatty liver is so common it's not even funny. It's part of the routine dictation macro for any ultrasound of the kidney, any ultrasound of the liver. It's so common that more often than not, you ask any radiologist, they'll tell you they see it all day long, every day, on CAT scan and on ultrasound and on CT that include the liver. So Roy Taylor's big memorial Banting lecture 2012. I don't know if you can specifically get this exact lecture on YouTube, but you can get a bunch of his lectures. So he's a real bright guy, real clear lecturer, and he's going to talk about how type 2 diabetes is reversed by diet alone. He's going to also talk, he calls it a two-cycle theory, twin cycles, 2 cycles. First of all, he describes as his so-called first cycle being accumulation of fat in the liver leading to the liver not being able to control blood glucose. And you'll have increased fasting blood sugar. He then talks about the pancreas accumulating fat and that being a problem. When you go low-fat diet, you can reverse these problems. The fat first reverses comes out of the liver, so that's the first thing that'll improve. He talks about different people having a different body fat threshold. That's why some people could be really fat and still not have diabetes, whereas others are pretty thin. And there's other reasons for that. Besides the body fat threshold, it's also that whether or not they're destroying their pancreas beta cells by these omega-6 oils from the Yamashima theory. Okay, here's another diagram from the same paper, the Banting 2012 lecture by Dr. Roy Taylor. He's from England. Gerald Shulman, of course, is from America over at Yale. Okay. So diabetes type 2 comes from eating a high-fat diet. We also say it's worse with high sodium in the diet, which is typical with a high-fat diet. It is made worse by eating a lot of industrial fructose, like all the sweetened beverages. If the person's sedentary, if they're in an air-polluted area, they have artificial sweeteners, and they're also, by not eating the plant foods, they're going to be deficient in potassium and magnesium typically, and that whole cascade of events pushes to worse and worse insulin resistance. So he draws this bicycle here, Roy Taylor, as if the high-fat diet coming into the mouth goes through the handlebars of the bicycle, if you will. And it's going to actually cause skeletal muscle insulin resistance first, but then he draws it here as going to the liver. Liver accumulates fat, then you get insulin resistance in the liver, so it can no longer maintain a normal fasting blood glucose level. It can't regulate it accurately. And it'll also start making more liver fat, as in fatty liver, and it'll send more fat into the blood, VLDLs, very low density lipoproteins, and triglycerides. And then that'll cause more atherosclerosis. And this accumulation of fat in the liver causes ALT to go up as a sign of injury to the liver. Well, this fat in the blood will eventually start accumulating in the pancreas, and it'll damage the pancreas cells. The pancreas beta cells are the ones in particular who make insulin. And once they can't make adequate amounts of insulin, the type 2 diabetes will get worse and worse, and blood sugars will drift higher and higher. So the best chance to cure is the sooner the better. The patient should eat a very low-fat, whole food, plant-based diet. Okay? And now here's a great quote from Roy Taylor. Type 2 diabetes is a simple condition of fat excess to which some people are more susceptible than others. And that's funny. It's funny because the typical ignoramuses will tell these diabetics, oh, you should eat ketogenic, paleo, all this nonsense. The problem is fat accumulation causing insulin resistance. And you can catch this, from hearing any of these other nutrition experts tell you. All the nutrition experts know this. Neil Bernard knows this. Dr. McNougal knows this. The mastermind experts know this. Anybody who's really studied nutrition a lot knows this, okay? So, also, people don't need that much fat. This good fat stuff is totally bogus slogan to get people to eat more fat. There's been studies where people have eaten less than 1% fat, and it was primarily omega-6 fats, and they were fine. The McKean study, the Winnett study, Kempner fed his patients 3% fat. They were fine, okay? You really don't need much fat in the diet. Now, don't get me wrong. It's impossible to eat this low of fat on any natural occurring diet. So there's no such thing as fat deficiency in a naturally occurring diet. That's relevant because all these, pathetic sick people are worried about getting their good fats. Okay, so how do you help prevent beta cell dysfunction? No oil, not one drop, especially not those omega-6, man. They're toxic, and they're taking out pancreas beta cells. No meat, not one bite. I mean, the average meat's like around 50% fat. Even the lean meat, lean chicken, is about 25% fat. And I can tell you, I know all these people, they're nice ladies, but they've been tricked by all the stupid stuff they've heard on TV and in the newspapers telling them, well, beef is bad, but it's good to eat chicken and fish. No, All meat is bad. There is no good meat. You need to know that. If you want to be healthy, you need to know that. Okay, Walter Kempner, Neil Bernard, John McDougall, Gerald Shulman, Roy Taylor, and many others have all shown type 2 diabetes reversible if a patient switches to very low-fat plant diet early enough. Exercising has a similar effect as insulin. When insulin is functioning correctly, it gets the cytoplasm glucose type 4 transporters in vesicles to go up to the plasma membrane. They merge with the plasma membrane, and then they create a channel through which glucose can enter the cell. Okay, lots of starches and vegetables. It's healthy to eat those foods. Also some fruits if you're exercising enough. Eat organic only to avoid the herbicides, especially like atrazine is toxic to your mitochondria, so that causes insulin resistance and diabetes. So here's Roy Taylor's paper, Reversal of Type 2 Diabetes, Normalization of Beta Cell Function in Association with Decreased Pancreas and Liver Fat, triacylglycerol, like triglycerides. Within 7 days, fasting blood glucose became normal. Liver fat decreased by 30%. So that's good to know too. The liver fat is the first one to get reabsorbed away. And that's what diabetes is. It's a fat storage disease. It's not primarily a glucose disease. That's real important to know if you want to get better. Okay, so that's the end of part 6 of diabetes on lectures on causes of obesity, with the focus in this past lecture on the theories of diabetes causation by Drs. Yamashima and Dr. Taylor.